Trigonometric integrals, level 4. In the previous video, we continued solving trigonometric integrals of the form sine of x raised to the power of m times cosine of x raised to the power of n, where both m and n are positive integers. Up to this point, we essentially covered 3 distinct cases. All of them required that at least one of the trigonometric functions contained an odd exponent. In the preceding video, we covered the third case, where both the powers on sine and cosine were odd. In this video, we will go ahead and cover the fourth and last case, specifically the case when both the powers on sine and cosine are even. Recall that in the previous videos, an odd power of sine or cosine enabled us to separate a single factor and convert the remaining even power in terms of another trigonometric function by using the Pythagorean identity. If the integrand contains even powers of both sine and cosine, this strategy inevitably fails. The strategy that we want to use when we are face to face with these types of integrals is to repeatedly use the following trigonometric identities. Sine squared of x equals 1 minus cosine of 2x over 2, and cosine squared of x equals 1 plus cosine of 2x over 2. These identities are modified versions of the half-angle formulas that you encountered in your trigonometry or pre-calculus class. The idea behind using these identities is to rewrite the even-powered functions into odd-power functions. It turns out that these identities do just that, since they convert even-powered functions into odd-powered functions of degree 1. These identities are also known as power reduction formulas. Then, from here, we go ahead and proceed with the integration step. Let's illustrate this technique by first going over a basic example. Find the integral of sine squared of x dx. Alright, notice that we have an integral that contains even powers of sine and cosine. In this case, we only have an even power of sine. But technically, cosine also has an even power. Recall that in this video series, we are dealing with trigonometric integrals of the following form. For this example, the value for m is equal to 2, and the value for n is equal to 0, which is technically an even number, since it shares many of the properties that even numbers possess. This means that we are dealing with a trigonometric integral where both the powers on sine and cosine are even. Alright, if we attempt to solve this integral by using the techniques from the previous video, specifically using the Pythagorean identity sine squared plus cosine squared equals 1 to replace sine squared with an expression in terms of cosine, we would obtain the following expression. Notice that we can easily take the integral of 1. This is just equal to x. But then, this is where we encounter our first problem. We now need to take the integral of cosine squared, an even-powered function. Now what? Well, we can try and use the Pythagorean identity once more and rewrite cosine squared with an expression in terms of sine as follows. Then, if we try to take the integral of the resulting expression, we end up with the following. Notice that the linear terms cancel out, and we end up with the original integral. All we did was to go around in a big circle. This is why you don't want to use the Pythagorean identity. Rather, you want to use the modified half-angle identities, also known as power-reducing formulas. So let's go ahead and use the following identity and replace sine squared with 1 minus cosine of 2x over 2, as follows. Notice that we started with an expression of degree 2, an even power, and ended with an expression of degree 1, an odd power. Now we are free to use the rest of our integration techniques that we learned from the previous videos to find the integral. So let's go ahead and factor out the constant 1/2, followed by a term-by-term integration, so the integral of 1 is just equal to x, and the integral of cosine of 2x requires a u substitution. So we let u equal 2x, and then we find the derivative of u with respect to x. Then we solve for dx. Next, we carry out the substitutions throughout, followed by finding the integral of the expression in terms of u. The last step is to substitute back the original expression for u. Doing that, we obtain the following. So the integral of cosine of 2x is equal to 1/2 times sine of 2x. Then we make sure we include the constant c. The final step is to distribute the constant 1/2. Doing that, we obtain the final answer equal to x over 2 minus sine of 2x over 4 plus c. Alternatively, we can also make use of the double angle identity. Sine of 2x equals 2 times sine of x times cosine of x to rewrite the sine of 2x expression in terms of sine and cosine. Doing that, we obtain an alternative answer equal to x over 2 minus sine of x times cosine of x over 2 plus c. Alright, let's practice some more and try the second example. Find the integral of cosine squared of 3x dx. Notice that this integral contains powers of sine and cosine that are even. In this case, the power on sine is 0. This is the reason why the sine term is nowhere to be found in the integrand. But this is not the case for cosine, which contains an even power greater than 0. This means that we need to make use of the modified half-angle identities to reduce the even power into an odd power. Before we carry out the half-angle identity substitution, notice that the argument on cosine is something other than x. In this case, it's 3x. As a result, we need to take into account this distinction in the argument when we use the half-angle identity. The way we compensate for this distinction is by observing that the argument on cosine in the right side of the identity is twice the argument of cosine on the left side of the identity. This means that when we carry out the half-angle identity substitution, we need to make sure we double the argument for cosine. So we start by substituting cosine squared of 3x with 1 plus cosine of 6x over 2. Notice that we double the argument from 3x to 6x when we carry out the half-angle substitution. Next, we factor out the constant 1/2. Then we go ahead and find the integral term by term. The integral of 1 is equal to x, and the integral of cosine of 6x requires a u substitution. So we let u equal 6x, and we also need to find the derivative of u with respect to x. After that, we solve for dx. Next, we substitute the expressions throughout. Doing that, we obtain the following. Factoring out the 1/6 and finding the integral of cosine of u, we obtain the following. Then we substitute back the original expression for u. So the integral of cosine of 6x is equal to 1/6 times sine of 6x. Making sure we add the constant c. After that, it's just a matter of distributing the 1/2. Doing that, we obtain the final answer equal to x over 2 plus sine of 6x over 12 plus c. Alternatively, we can use the double angle formula and write the answer in terms of sine and cosine. Once again, we need to take into account the argument of the trigonometric function. For this identity, the argument of the expression on the right side is half the argument of the expression on the left side. So we can replace sine of 6x with 2 times sine of 3x times cosine of 3x. Simplifying the expression, we obtain an alternative answer of the integral equal to x over 2 plus sine of 3x times cosine of 3x over 6 plus c. Make sure you take into account the argument of the trigonometric function. When using identities, you might need to take the expressions inside the argument into account. In general, if both the powers on sine and cosine are even and non-negative, we make repeated use of the following half-angle identities so that we can convert the integrand into odd powers of cosine. Then we proceed by applying the same techniques that we used for case 1 and case 2 from the previous videos. In addition to the half-angle identities, it is sometimes helpful to use the double angle identity sine of 2x equals 2 times sine of x times cosine of x, especially when we solve for the product sine times cosine. After all, we are dealing with integrals that contain products of sine and cosine. This is the fourth and last case that we will cover in this video series of integrals that contain powers of sine and cosine that are greater than or equal to 0. Alright, now that we know how to use our new identities to solve even-powered sine and cosine functions, we are ready to solve integrals that contain products of sine and cosine that contain even powers. In our next video, we will cover slightly more complicated case 4 integrals.